All right, good morning, everybody. I think we're all about ready to start here. It's 7 o'clock in beautiful Honolulu. I'm not at the beach, fortunately, but I could be. The schedule has a 10-minute welcome, just like yesterday's, and I don't think we need 10 minutes to do that anymore. We'll just say a few things about how things are going so far. So we seem to have been able to keep up with most people's questions in Slack, so that's good. Keep posting in Slack. Keep sharing scripts when you have trouble. It was brought up the comment that we didn't really talk about how to read the documentation. That's true. We assume that people knew documentation because we do, but of course that's not true. So the way you look at the man pages is that there are a lot of things in the man pages, especially at the top of them, that lists all the options that a module can take, and many of them are in square brackets. And what the square brackets mean is that that option is optional. It's not required to be used, but you can use it to get a special effect. And if you want to use it, then you don't type the brackets, you just use the option itself. And the best way to get a sense for how you translate from that synopsis to an actual command is to look at some actual GMT scripts. And there are some examples at the end of all the man pages. So that's sort of how the syntax works. So yeah, that's a big learning curve in the beginning, how to read Unix man pages and how to figure out from that how to make a command. But the examples we give, you'll see there's no brackets there. It's all just plain options or not options being used. So today is second day. We're going to switch gear from sort of very general plotting lines and maps to stepping into some more science data. So we're going to look at seismology and beach balls and how to plot focal mechanisms. And then we're going to look at some more geodesy applications with plotting GPS vectors. And then after the long break, we're going to try to make a couple of animations to see how we can do that in GMT. And then we're going to start on the final projects that will be very individual. So it's up to you what you want to do there, and we will help the best we can. And you should really take advantage of the breakout rooms and get help from your fellow attendees, because they are often in a better position to help you with that than we are. So that's sort of the lay of the land. The recordings are being finalized from yesterday. They will be up soon. Hopefully in a day or so after the course, we will put all the material up there for everybody to see. So that's sort of where we headed. And I think that's enough of me talking. We'll start with the first session, and that's going to be on seismology by Dongdong Tian. And Dongdong, you might want to hit record if you haven't already, and it's all yours. Go ahead.
Okay. Thank you, Paul. Thank you for Paul giving me 5 more minutes. Okay. So this is the material we are using today. So in GMT, there are 4 seismology modules. Like shown in this figure, there are Mecha module, which can plot beach balls on maps, a Cope, which can plot beach balls on maps cross sections, and the Polar, which actually plot the first motion priority. Seismologists usually use this data to constrain the focal mechanism, and also the second module, which can plot the seismic waveforms in second format. These two are too technical for geodesy users. So in this session, I only focus on 2 modules, Mecha and the Cope, which plot beach balls. So if you know very little about focal mechanism or beach balls, I suggest you can watch this video. It's only 6 minutes. And I think it's very good for people who don't know much about focal mechanism or beach balls. So I will first give a very brief introduction to focal mechanism and the beach ball. Focal mechanism actually is just describe the movement of the fault which generates the seismic waveforms. So there are 3 basic parameters to describe the geometry of the fault plane and the slip direction, like the strike, dip, and slip, the 3 angles. But how can we visualize the fault geometry on maps? We cannot just print the 3 angles on a map. It's not intuitive. So we can use beach balls. Beach ball is just a graphic representation of focal mechanism. Here are 3 basic fault in seismology, and this is a strike slip fault. This is a normal fault. This is a reverse fault. And these 3 figures are the beach balls for the 3 faults. We can see that the 3 beach balls are totally different. So if you have some basic knowledge about beach balls, about focal mechanism, then when you read the beach ball, you can actually get the strike, dip, and rake of the fault. Then you know the geometry and the fault orientation and the slip direction of the fault. So in this study, in this session, I will use these 3 basic faults as an example. This is the example data I will use in this session. I will first explain the meaning of each columns. The first 3 columns actually give the location of the earthquakes, the longitude, latitude, and the depth of the earthquake. And the 4 to 6 columns give the strike, dip, rake of the focal mechanism. And this column is the magnitude, which describes how big is the earthquake. And the last column is just the title of the earthquake. So next, I will show you how to use the mecha and the cope command to plot the beach balls. First, we need to prepare some data. So we need to copy paste the data and save it into a file. So let's first copy. And we need to open VS Code. So after open VS Code, I first need to run terminal and new terminal. So this is editor, this is terminal. I'm currently in the GMT course seismology directory. ls is empty. There's no file in this directory now. Then I new file. Okay, I will save this data into this file and save it. Let's just call it mecha.dat. File. So this is the file we'll work on in this session. Let's just check that. ls, we can see the file in this directory. Now let's create a new script. Like what we did yesterday, just shebang beam bash, then GMT begin. So we give it a name, beach ball. Okay, here we will use PNG format, then GMT and show. Okay, so this is just a very simple simple example to begin and end a GMT figure. And let's save it to a new file. Let's call it beachball.sh. Again, we need to confirm that the script and the data are in the same directory, which will make the script much easier. So now, how can we plot the data in this? How can we plot the beach balls in this file? We just want to use GMT mecha. And we also need to give the name of the data file, mecha.dat. And then we need, like what we did yesterday, we need to give a projection. -J, I will use Mercator projection, and the size of the map is just 15 centimeter. We also need a frame. And we also need to give the region of the map, -R. So from the data, actually, we can see that this is the longitude and latitude of the earthquakes. So we need a region which which include this all the earthquakes. So like we can have a left side 110, and the right side we can have 120, and the minimum longitude is 30. The maximum is 35. So this is just what we did yesterday. GMT base map. We all need this -j, -b, and -i options. For Mecha module, there's an important option -s. So because there are many different ways to describe focal magnetism, so we need to tell GMT what's the format we are going to use. So we use -s. A means we'll use the Archi-Richard convention, which means we use just like this file, strike deep rake to describe focal magnetism. And we also can give the size of the beach ball, 2 centimeter, which is the size of the beach ball. Now let's save this file and run it. Bash beach ball. Okay, so now we get this file. Okay, I probably want to have a smaller figure, 10 centimeter. Okay, so this is a beach ball we are plotting. Actually, we just use one single command to have this map. And you can see that the beach ball is a little too large for me. So I can just change it 2 centimeter to 1 centimeter. Then I can run this script again. Okay, it's smaller, it looks better now. So this is just the basic command to plot beach balls. The most important one is -s options. Then I will try to change the map a little bit. I will first copy paste this command, just back up and comment this one. Okay. Go to this like this. So from this figure, actually, you can see the location of all the earthquakes. And you can also see the beach balls, which describe the focal magnetism of the fault. But we don't know the, and we also can know the magnitude of the earthquake. So you will look at the beach ball, you will see that the size of the beach ball is different. So what's the 1 centimeter here? It's the beach ball size for magnitude 5 earthquake. So if the earthquake is larger, like magnitude 6, then we'll have a larger beach ball. So for small earthquakes, the beach ball will also be smaller. If you want all the beach balls has the same size, you can use -m option. So how do we know that? We need to go to the documentation of the Mac modules. So you can just go to terminal and run GMT docs mecha. Then you will see the documentation for the mecha modules. Let's go to the -m option. It says that use the same size for any magnitude, and the size is given with -s. So here I can use -m. Then according to the documentation, then all the beach balls should have the same size, and the beach ball size should be 1 centimeter. Let's try this. Yeah, you can see that all the beach balls have the same size, right? Okay. I will leave this comment this line and copy paste this one. So, and I will run this again. So this is the original map we got using the first command. So you will see that it's just a white and black. The compressional part are black, and the extensional part just white. It's not that beautiful. So can we change the color? Of course we can. We can still go to the documentation, and there is a -E, which can select the filling for the extensive quadrant, which default is white, and also -G here, which selects the filling of the focal mechanism for the compressional part. We can change the color like -E. We can use a color like light blue. And for the compressional part, we can use -G, right? If we run with this script again, so you can see that at least it's beautiful now. Okay. If you look at the figure, you will see that for each beach ball, there is a title here, just above the beach ball. We can actually control the properties of these strings, these titles. I will break this into 2 lines. So how can we constrain the properties of this text? We can add more modifiers to the -S options. So again, we'll go back to the documentation, -S. Actually, it says we can use +A and some angle, +F, give some font, +J and give the justification code, and +O to shift the title relative to the beach balls. We can try them. So we can have a +A 30, then run the script. So you can see that the titles rotate counterclockwise by 30 degrees. We can also change the font and the color of and also size of the text. Like we can increase the font size by 16 point, and we may want a blue color. Okay, so this is what we will see for maybe smaller, 14 point. Okay, just like this one. Again, I will comment this line and this line, and I will also go back to the the simplest command. Okay, so if we compare this figure and this data, we can see that from this figure, we know the location of the earthquakes. We know the location, and we know the strike deep rate from the beach balls. And we also know the magnitude from the size of the beach ball, but we don't know the depth of the earthquake. It's not showing in this figure. One way to do that is we can give different colors based on the depth. This is done by -J option. If we go to the documentation, it says give a CPT and let the compressional part determined by the Z value, the depth value. So we can use -Z option, but we need to give a CPT file. So we can create a CPT, use GMT, make CPT. Then we can choose a CPT like JET. And because the depth range, the depths of the earthquakes are 15, 25, 45. So we can have a beach ball covering the depths from 0 kilometer to 50 kilometer. Then, so now we have a CPT file, and we'll use this CPT file in this command. If we run this script, we will see that now the beach balls have different colors. But what's the meaning of the color? So how how can I know the depth from these colors? That we need to use the GMT color bar, just like what we did yesterday for the Earth relief data. And we have a frame. I can run the script again. Okay, so now it's clear. By comparing these colors, we know that this earthquake actually is 15 kilometer depth, and this may be 25, this may be 45. So this is what we will plot actually a fancy beach ball map. So this is all about the map command. Sometimes we also want to plot beach balls over cross sections. Like, for example, this is the map view of the beach balls. When we want to draw a cross sections like this one, and we want to plot all the beach balls on these cross sections, then we'll use the GMT cope command. I will create a new file, GMT new file. New file. Again, we need to use shebang beam bash GMT begin beach ball cross long name cross section PNG format, then GMT and show. Save this file to beach ball cross section .sh. Again, we need to confirm that the script is in the same directory with the file. Then we'll use the GMT cope command to plot the beach balls. GMT cope, we also need to provide the data. Again, we need to provide the projection. For a cross section, the x-axis is no longer the longitude. The x-axis is the distance away from the starting point of the cross section. The y-axis is usually the depth. So now we need a linear projection minus jx, and we want a frame. We also need to give a region of the map, but we don't have to, because currently we don't know the limit of the region. So just like micro command, we also need to use -sa 1 centimeter, which is has the same meaning in cope command. We use the Archie and Richard convention. The beach ball size is 1 centimeter. The most important option in cope is -a. Again, this option is complicated, so I will go to the documentation. Run GMT docs cope. It will open the documentation in here. I will click the -a. So -a option actually can determine the geometry of the how we can get the cross section. There are many different ways. We'll use this one. So we'll use -a and a. So for this cross section, we need to give the location of the starting point and the end point. Like we can give 111 and then 33. And the location of the end point is maybe 119 and 33. So these are the 4 parameters here. We also need to give the deep angle of the cross section. So usually we have a vertical cross section, then we'll have a 19 degree, which means the cross section is vertical. And this is the p width of the cross section. So there are maybe many beach balls. Like we have 3 beach balls here, but there may be other beach balls here. But we do not want to plot all the beach balls. We just want to focus on the beach balls which are not far away from the cross section lines. So like the distance from this earthquake to the cross section may be 1 degree, about 100 kilometer. Again, here is about 100 km. Sorry, it's close to 100 meter. 100 meters. So we can use like 500 meter to include all the three beach balls. And then there are another two parameters, dmin and dmax, which are the depth range. Do we want to include all the depth range? Yes. So we can, the minimum depth is 0 kilometer and the maximum depth is 50, or you can use 75. That's okay. So this is all the basic parameters to describe the cross section. And again, here we can add the plus F, which can automatically get the frame from the parameters. We'll use plus F. Let's see what will happen here. Bash beach ball cross section .sh. Okay. So this is a cross section. So this is what we got using the GMT code command. If you compare these two figures, you can see that they are totally different. This is a strike slip. We can see the shape of the beach ball is different because this is a map view, this is a side view. The x-axis is the distance from starting point. So this is 0 kilometer, and this is about 700 kilometer, and this is the depth. So I will close this one. But I'm not very satisfied with this figure because I want to have a custom region. So I need to minus, I can now, because now I know better about the data, so I can use minus R, 0, maybe 8 kilometers. And the depth range I can have from 0 to maybe 100 kilometer. And then I need to remove minus plus F. So GMT will use this region. Then if I run the script again, oh, sorry. Let's see. Oh, no, it's here. Oh, sorry, I forgot this break line here. Oh. Okay, here, this is the x minimum, x maximum, and depth minimum and depth maximum. And this is also almost good, but we usually want to reverse the y-axis because we usually want to have a depth, 0 depth here and 100 depth here. So we need to reverse the y-axis. It's done by modify the -j option. So 10 centimeter is the width of the map. Then we can have a slash. We can have a 8 centimeter, which gives the height of the map. And if we change it to a minus value or negative value, we can reverse with the y-axis, bash beach ball cross section .sh. Okay, so this is what we'll have using the GMT code command. We can also use the -m, -e, -g option to modify the details. I will not go to much details. Okay, I will close here. Okay, so now we can do the group exercise. But before we do that, we need to know how can we get the focal mechanism solutions. One source of the solution is from Global CMT. So this is a link to the Global CMT project. It includes all the earthquakes from 1976 with magnitude greater than 5.5. So this is a map of the global earthquake focal mechanism. You can see that. I believe it's not plotted using GMT, so it's not good. So you can actually replot this figure using GMT. And we scroll down to this link, GMT catalog web search. Then you can select the events based on the date, magnitude, and the locations. For example, we can have 2020, we can have 13 days since the start of this year, and we want to magnitude greater than 6. So this is our global earthquakes, and then we can select the output. There are 6 different types of the output. We will use this one, GMT PS maker input. Do not use this one because this one is old format. In this format, it doesn't contain the depth of the earthquakes. So I will, and this one is what we are using here, GMT PS maker input. And if you click the down button, you will see this website. This is the search criterion we just used: the date, the location, the depth range, and the magnitude. This is the result. The first 3 columns are longitude, latitude, and depth of the earthquake. And the next 6 are the 6 elements of the 3x3 moment tensor. It's just another different way to describe the focal mechanism. And this is the exponential part of the scalar moment describing the magnitude of the earthquake. And then that's the name of the earthquake. So you can just copy this from this line, copy, paste all the solutions, and save it to a new file. Then you can just plot all the beach balls using GMT Mac and GMT Cope. So then we go to the group size. So group exercise. So you can plot this 2 figures, map view using GMT Mac command, and the cross-section view using the GMT Cope command. So you need to select the region and then go to the GCMT website and download the data, download the solutions, and make the beach balls colored by different depths. And you can also use the grid image command and the GMT color bar command, and also plot command to plot the earth relief, the lines, and the strings here, and you will get a figure like this one. And then you can use GMT Cope command to get a depth cross-section. But you need to note that because we use a different format, we use the data from global CMT, so we have to use -SD, not -SA. And so one more thing is that because the global CMT solutions have the event title for all the earthquakes, then you will see that there are maybe 100 earthquakes here. You will see 100 beach balls and 100 titles. That's not what we want. So you can use -I0-9, which will select only the first 10 columns. So you will skip the title of the earthquakes. You will get a figure like this one. Okay. I think that's all.
All right, so I'll be covering a little bit on the session about it says for plotting for geodesy, but really a lot of these geodetic data materials are already covered from yesterday's plotting. Either you are plotting symbols, lines, or gridded data. Here we're gonna mainly be like learning about plotting vectors, usually associated with GNSS data. So if you go to this GitHub page, I think I posted a link on the Slack chat room. If you go there, here are the notes for the plotting with vectors. And there's a set of data that I'd like you guys to download before we really start the second part of this session. It's on a Google Drive. You can either find the link on the web page, which is this one, or you can go to the Slack chat room. I also attach the link there. So we'll be mainly covering, let me make this a little bit larger. So we'll be mainly covering 2 parts for today. First is to learn how to plot vectors, learn a little bit about the vector attributes, mainly associated with one of the option in GMT, which is the below command with -SE option. And then we're going to plot a vectorized deformation field as an example or testing cases, and it is from the Ridgecrest earthquake sequence. So first, we're going to talk about vector attributes and some examples. So this part we will experiment with mainly the -SE option in the reload command. So -SE option has a few attributes behind it. First is a velocity scale, and then the confidence level, OER plot, and font size. Also, this small e letter represents ellipse, I think, for the uncertainty circles appended after the vector. The input file requires you to have at least 7 columns. That is longitude, latitude, or XY, and then east, north velocity, east and north standard deviation or sigma or uncertainty, and then the correlation between the two uncertainty. You can also append a site name at the end. And then those letters will show up like next to the vector you're plotting. For the arrow, like you would like to append to this vector, it is mainly controlled by this -A option appended behind the reload command. And it has a few things that you can add after the -A option. The first, of course, is the size of the arrow. I think that's the size of the arrowhead. And then with the +A, you can change the apex of the arrow. The default is 30 degrees. You can change it to a larger, like a fatter arrow or a narrow arrow by changing the number. And then with the +BEM, it represents at the beginning, end, and the middle. And then you append a TCAI to represent whether you want a terminal line or a circle or arrow or tail for that head. Then with +G, you can fill the arrow with colors, and the +P to change the width of the vector line. Note there's also a -W that can change the pen for the plotting, but it also controls the width of the uncertainty ellipse, not just the vector line. And with the +L or R, you can plot only left or right half of the vector arrow. And the +N will allow you to normalize the vector plotting based on how long your vector is. So next, we're going to start with some examples. If you go to your terminal, I mean the VSC, now we are here. I already downloaded the stuff into this GMT vectors folder. So I think we're going to start there. File, new file. Oops. I'll just use Command N. And then we're going to save it to this GMT vectors folder. Guess it's here. Then we're going to call it plotVec.sh. And then save it. As usual, you need to input the data for the vector. So we're going to start with the same thing that is used in this course many, many times, which is echo. We want to plot maybe just a very simple vector. On it to start from 0, 0 with 1 and 1 as the velocity. And for now, we don't put any uncertainty on it. So all of these are zeros. Let's call it temp.dat. It's just a random name. Also, I would like to set up some parameters for the plotting. I'm going to call it GRB equals. These are the -J option. Here we're going to use just Cartesian in scale 3, 3 -R. We're going to, since it's a relatively small arrow, so we're going to assign a very small area also. And then with the -B option, I'm going to give it A1, F1, G1. So with the annotation frame and grid line both being 1. So we're going to start with GMT begin. I want it to be PNG. GMT end show. So here we're going to use GMT reload. Oops. GMT reload temp.dat, and with the $JRB for our specification. And then with the -SE command, we want to plot it for now, just the full scale. So I'm giving 1.0. Confidence level, maybe 0.65. Font size, 10. I want the width of the stuff to be 1 pixel. So if we save that, then we type bash that file. And there we go. You get a vector from 0, 0 to 1, 1. Of course, there are more parameters that you can tune with. So let's close this. For example, I want to add the uncertainty scale for this. Let's change it to 0.2 as the standard deviation. What's going to happen if you rerun this same script? It gives you an uncertainty circle over here. Another thing that you can try is to change this confidence level, because I think the underlying assumptions for this uncertainty plot is that it's the 65% corresponds to 1 sigma. That is probably Gaussian distribution. If you change it to, for example, 3 sigma, that corresponds to 99 of the confidence level. And the circle becomes like 3 times larger. Of course, you can also change the correlation between them. For example, I want 0.5 correlated. If it's fully correlated, it's going to be just 1 line, right? The ellipse won't have any like thickness. Now you get like a tilted ellipse over here. So let's change this back. I'm going to make this slightly smaller, so when it pops up, you can still see the code. Oops. So that's it for this ellipse. So let's change this to 0.65 back. It's a little bit wider so you can see the code. So next we're gonna play a little bit with the -A option. So remember that the -A option allows you to control the arrow. First, we're gonna give it a different size. For example, we want it to be like 10 pixel with an arrow at the end. You can choose the for smaller a over here as a fancy arrow. Like that. Or you can change it to a larger a for a plain arrow. So just like 2 segments. And we can also plus, maybe at the beginning, we also want a tail of the arrow, so it will become a real arrow. If we do it again, now you have a little tail over here. Maybe I also want to fill the arrow with some kind of color. So with the +G option, I want it to be blue. So now our arrow becomes blue. There's another thing that you can control with the +P option. I think it controls the width of the this segment itself. For example, I want to change to 5p. Now this is becoming thicker. It doesn't look so good though. So you can actually play with all of these and get an arrow that you like. Another thing that you can control is the +A option, which changes the fatness of the arrow, like what is really the angle of that arrow that you're gonna do. If you change it to +A90 and save it, then run this again, now you get a really, really fat arrow. It also affects the tail as well, you might have realized. So these are some of the experiments that you can do with plotting these kind of arrows. Next, we are gonna like do a real demo test using the data that you guys might have just downloaded, which is inside this folder. I'm going to describe a little bit like what each of these are. So the gps.dat is a file that has all the GNSS solutions for the Ridgecrest earthquake. It has some fake uncertainty in it just for plotting purposes. If we had this file, you're going to look at the first few lines of this file. You see that it has the longitude, latitude, east velocity, north velocity, uncertainty, and correlation. The numbers behind are made up by myself. And then you have de.grd and dn.grd. These two are actually gridded data. They are derived from an earthquake source model. If you go to the GitHub page, it has a link on it, says on the Topax side. It has some like interferograms and data and models, or even Coulomb stress change from this earthquake. Feel free to go through some of those. Many of the plots there are made by GMT. And also a CPT file, it's a color table. And then this dmdsump.grd is a digital elevation model file that records the elevation like numbers. And then this new faults. Basically, it's just a fault file that it's being divided into small segments. If you do a head on that new faults, you see it has a bunch of these segments with the -L in the front. Most of them are untitled. So these tables can be read in GMT and to be used to plot small segments for like your fault locations. And these new faults are identified from a phase gradient technique that probably we're going to cover in the next few days with the GMT SAR short course.
Eric?
I hear someone's talking.
Sorry to interrupt.
Yeah.
Someone's asking if you could either maximize the script or maybe break the line so that they can see the entire code.
I see.
Yeah.
Sorry.
Thanks.
Thank you. Okay, so we're going to start plotting for these data sets. So we create a new file. Let's save it. Maybe called plotmap.sh. But before we get started, I want to set up some of the parameters as usual. So I want the DEM to be called DEM dsum.grd. This is the DEM file name, just to make the script cleaner later on. And GPS has a name of gps.dat. And the range that I'm going to plot. So this is an interesting command. So bash allows us to assign parameters from those terminal command lines. The only thing you need to do is to type in this really strange quote on the left-hand side of your number 1, that key on your keyboard. And then you type in command gmt grd info -i $DEM. So we can actually try it here. What does this command really give you? So let's copy this line here and set up the DEM and copy the other line here. Oh, I'm sorry. I shouldn't put the RR in front. Just get this GMT grd info -i- on your DEM. This gives you the range information for that grid. If you are lazy and don't want to really like input all the numbers, you can use this handy command. Then the output equals, I just want to call it maybe demo. And then format to be PNG files. So next we're going to start plotting. So GMT begin, GMT end show. I want the output $format. So we're going to first start plotting a base map, which is just with frame and nothing's in it. And we're going to use the Mercator projection. 6 is probably good. This is the range information you just get from the GMT GRD info command. And then we want the frame to be maybe 1 degree with the frame of 0.5 degree. Then if you save this script and then bash plot map, now you get a map that has nothing in it. The next, we're going to start plotting the DEM, which is the digital elevation model. The DEM that we are plotted here is actually the height above a ellipsoid over this region. And normally, when you talk about DEM, it's usually like sometimes height from a geoid, but anyway. So if we type GMT GRD image, like what Leo showed yesterday, $DEM, your file name, with the -I option, I want some shading on it so that it looks nice. And then with a color map called dem.cpt. If we save that and then plot it again. It doesn't look so well, does it? So maybe I want to tune a little bit about the gradient, and it looks a little bit coarse as well. So the default sometimes may not work very well. So I'm going to add something behind the -I option. The +n allows you to compute a gradient with a specified format. I'm going to use the T arctangent transform with a normalized scale to maybe 0.3. Oh, still looks really white. Why is that? So probably the DEM is kind of too saturated. The numbers in it, it's not really like supposed for this DEM. So we're gonna make something like before to change this DEM. The command that we're gonna use is called make CPT. And we're gonna make a new color table based on that. So the -T option allows you to choose the range of the CPT file that you want to plot. Here we're going to use 0 to maybe, I don't know, 2000 with the interval of 100. We want to make it continuous, and we also want to make it saturated and output that into a file called dem2.cpt. Then we change this part to 2. If you save it, you recompute. Looks slightly better than before. You can further tune because I don't want this part to be all white. So I'm going to change this color to maybe 3000 so that the numbers are scaling up a little bit. If I save that, looks much nicer than before, right? So next, we're gonna plot the coastlines because this is in Southern California. You might have realized just based on the topography, you see that this part might be the San Andreas, that might be the Garlock Fault, and that's Los Angeles, and this part might be ocean, but it's not plotted as ocean. So we're gonna use the coast command that we learned yesterday. So GMT coast. I want all of the boulders to be plotted as 0.5 pixel and black with dotted dash line. And I want to fill the water with light blue. The -D option allows you to plot at different resolution or definition. I want a full definition. if you save it and rerun the bash script, you'll see that, oh, this part of the water area is plotted as light blue. And you also get the border between California and Nevada over there. And you also get the small lake inside the map. So next, we're going to insert something. So GMT itself is not just for plotting. It also is able to process data. So the command that we're going to use here is called GRD sample and GRD to XYZ. So the GRD sample allows you to resample the grid info. What we're going to do is that we're going to downsample. So this is the eastward deformation from the earthquake. It's de.grd. I want to sample it about maybe every 10 kilometer. I want an arrow. So I'm going to use 0.1 degree. And with the -G option, it allows you to output the grid. Let's call it temporary e.grd. We're going to do the same thing for the north deformation field. With the -I sampling 0.1 degree -G temp n .grd. Then we're going to convert these into tables for the below command to plot it. The command we're going to use is called grd to xyz. We're going to give it the grid name and then output it to, it's going to be longitude, latitude, and the deformation. So we're going to just name it LLD or something like that. We're going to do the same thing to the north component. Next, we're going to use some Linux command. One of them is called paste. So for example, you have two tables. Both of them has maybe 3 columns. But I don't want to attach one of them to the end of the other one, because we learned that you can use the cat concatenate command to do that. If you want them to be side by side, for example, I want to convert this 2 3-column table into 1 6-column table, you can use this paste command. This is going to give you a 6-column table. And you're going to pipe that into an awk command. So awk is a really powerful tool. It allows you to manipulate data tables in a really quick fashion. Since we already have 6 columns, the table we want is sort of an input file for the below command. Remember, there are 7 columns needed. You need the longitude, latitude, east-north velocity, uncertainty, and those others. So we're going to print $1 means the first column, $2 is second column. So this is the longitude, the latitude from the first file and the east component. Then your north component is in 4, 5, 6. It's in the 6th column, right? Give it $6. And for the rest, we don't really need it. So we're just gonna output zeros like we did at the beginning for the other test case. Then we're gonna output that file in a name called maybe deformation.dat data files. After that, you'll be able to get this data table that can be read in with the below command. So next, we're gonna plot the data. So GMT below. We want to input file is defo.dat. What attributes are we going to use? We want these arrows to be a little bit thinner because we have too many of them. So let's use the -W option with 0.1 pixel, which is very, very small and black. We also want the -SE option, since you might have realized you probably don't want to plot them at full scale because the deformation.dat, those grid are in quite large numbers. So I want to plot them into 0.02 scale, 0.6. Well, the numbers at this confidence level and the fonts don't really matter because you're not going to plot them as they are like represented by zeros here. And then we specify the -a option for the vector attributes. Maybe I want them to be a little bit larger, like 10 pixel size. I want the arrows to be at the end as plain arrows. Also, there's another option allow you to normalize a little bit, which is this n plus n10. We're going to see what this number really affects when we have the plot. So if you save the script and make the plot, it's going to, oh, there's an error. But before we get into that error, first, it's going to warn you that the sampling interval is not large enough. So you might get some aliasing. So, but this is normal because the grid itself has pretty dense sampling. Well, this 0.1 is much larger than its sampling. So we're going to warn you about aliasing, but that's okay. Let's see where the error comes from. Oh, I forgot to tell it to print. So if you add the print in front of this $1, then it should work. If you rerun the script, you see a lot of arrows are being plotted on this map. The deformation says it's going this way on the corner there and going that way on the corner there. So let's play a little bit with this -n option. If it deleted or just comment it out with the hashtag, we'll see what happens. So you see all the arrows are plotted at the same scale, which is a little bit ugly looking. So sometimes you do want to normalize your arrows a little bit. So let's add it back. So you have this deformation field that is already represented by these vectors. You also want to plot where the fault is. So next we're going to plot the fault onto the map, the sort of the rupture locations. The command we're going to use is called plot. It used to be called psxy or something. And then the file name, if you do a ls inside the folder, it's called new faults.gmt. And I want to plot them with the pen of maybe 0.5 pixel with red color. If you save it and rerun this script, now you know where the rupture is. Finally, we're going to plot the GNSS data onto the map. Again, we're going to use the willow command. Remember the file name, we set it to be $GPS. I want to plot them in slightly thicker because you want it to be sort of standing out, maybe with 1 pixel, with blue colors for the lines. Then the -G black. I want to fill it with black. -SE option. We want the arrows to be scalable with that earlier plot. So we're just going to copy this to the -E option. Then again, with the -A option, 10 pixel plus E. This time we're going to plot the fancy arrow and also normalize it with the same length scale. If you save it, then bash plot map. Now you're getting all the GNSS vectors plotted on top of the map. You can actually compare some of them. For example, you have an arrow here that lies in between this one and that one. It largely follows the deformation field. So that's pretty much to it. All the demonstrations are done. But still, you can add more things. For example, oops, kind of too big. Maybe I should go back to this part and make it larger. You can add more things to the map. For example, the epicenter. I want to plot a symbol with a star with different colors filling in, representing the 6.4 and 7.1. I also want to plot the focal mechanism with a line linked to that epicenter. So that'll be a bonus challenge for this session. Also, there's another bonus challenge for this session, which is asking you guys to plot a strike slip symbol. So this is a right lateral strike slip sign plotted from the Willow command. So this is another bonus challenge. So I guess we'll get into like groups. Any questions? Or I think you guys are posting stuff on Slack chat room. So
yeah, thanks, Eric. So Melissa will start up the work groups, and we will monitor Slack and try to answer as many questions as we can.
All the stuff are like recorded in this GitHub page. So if you feel that you're missing anything, simply go there and all the details are in it.
Okay, so I have shared my screen, so you should be able to see it. It's a gigantic TV, so hopefully I can scale up fonts as needed. So we'll talk a little about animation. These slides are also linked from the GitHub site, so you can always go there and do it on your local machine if things are unclear. Just a little plug, we have a YouTube channel for longer movies that we won't have time to run today. So the whole thing with movies, it's a pretty simple concept. A movie is just a bunch of still images that are played back in some order. And GMT makes still images, so it's not too much leap of faith to imagine that you can make a bunch of images that are slightly different and then play them back, and now we have a movie. The trick, of course, is to make the frames slightly different. Because if they're all the same, let's say we just made 10,000 identical GRD image maps, that would be a really boring movie. So the trick is to be able to change things as we move forward. So there's two sort of timelines here. One is the playback time of the movie, which is how many frames are being shown per second. And you might be familiar with regular movies at 24 frames per second, but often you will have lower frame rates for science data that may not change that quickly. So you just slow it down in a sense. And then there's the animation time, which is the actual time that each frame represents. So this could be anything, right, from millions of years to nanosecond, depending on what you're trying to show. So you have to be aware of these two different type of times and how you want to present things. Now, the thing with the movie program in GMT, which is the one that we're going to use to make a movie, it tries to make it simpler for you by eliminating that loop over time that you're going to have to do, in a sense, to make changes and run your script again and again with slightly different arguments. To set that up manually is really tedious. So the movie was built to make this simple. And it does add a little sort of abstractness to the whole thing, is that you have to think a little bit more like a programmer. And there are special variables that movie maintains that changes with frame number. And we're going to take advantage of that. And then there are other things that are constant. So this is kind of a complicated topic in general, so we'll just keep it really simple. You just have to be aware of a couple of things. So when we make a movie, we basically have a different kind of page size than you normally think of. We often like to think of movies in 16:9 format or 4:3 or something. And if you choose those pre-formatted formats, basically, then you are selecting a paper size, which you kind of need to use to compose the size of your plots that are given by these two dimensions, 24 centimeter by 13.5 for the widescreen and 18 by 4:3. But if that doesn't work for you, you can select your own format completely separately. You're basically specifying a custom paper size that you want to plot onto, and then use that for a movie. There are some special shell variables. We're going to write this in a bash shell, and there's some variables that are available to you to use, even though you never set them. They're set under the hood. And these are things that are constant throughout the entire movie. So if your script needs to know how many rates, how many frames are we building, or what is the width of the canvas, you have these variables that are there that you can use in your script. The key part, though, is variables that actually changes with each frame. So some things that are obvious, the movie frame number is going to go 0, 1, 2, 3, 4, 5. That's automatically incremented for you. So you just have to abstractly think that I'm going to use make a plot for frame number X, whatever X is. And there are other variables that are automatically set. We will use some of them today in the simple case we're going to explore. And particularly the movie column is an important one. So column here can be column 0, column 1, column 2, and it refers to a data file that you may prepare for movie to use. So think of a table with rows and columns, and the rows are the frame numbers and the columns are the columns. So as you make the movie, we will pull out the right column from the current frame, and you can use that variable to plot something. So this sounds very abstract, so we kind of have to look at an example for how this actually works. So we're going to do a very simple movie, and it's not super exciting, but it is a movie. And it's basically making a movie of a spinning Earth using the orthographic projection, JG. And we're going to, and that sort of basically shows you a view from infinite space, basically infinite distance. And you specify the longitude, latitude of that center point. So we're going to do that, but then we're going to want the longitude to actually change as the frame number changes. And to make it super simple, we'll let the central longitude equal the frame number. So it's going to be 0, 1, 2, 3, and so on. And because making movies is taxing your computer, we'll keep it very simple. We'll make a short one, just not even 1 frame, so just a quarter of the Earth, basically. And we'll make a small format movie, let's say the 360-point movie. We do this because it takes a long time to generate all these frames and put together into an actual product. So offline, you can change this and knock yourself out with making 4K movies if you want. It's just going to take a little longer. So I'm going to switch to my editor here and start a new file. New file, yes, we can do it. And do the shebang, bin bash. And I'm going to write a little comment to myself. Simple frame script for spinning Earth. Okay. So the map of the Earth is just going to be a very basic coast command. So we know this already. We know how to make coast commands. So we do GMT begin and GMT end show somewhere. And then we're going to put something in between, obviously. So I'll just save this for now. So I have a file name. I'll call this earth.sh in my GMT course folder. And now we're going to put something inside here. So I'm going to make a, let's see here. We're going to make a map. So GMT coast. This is going to be plotting the entire Earth. So we're going to use -r lowercase g for the whole globe. We know we have to paint the land and the ocean if you want. So if you don't like my colors, you know, you can pick your own colors. I'm going to make the land, wheat again. I don't know. I like wheat right now. And then I'm going to paint the ocean a different color. Maybe what, blue? Blue is very dark blue. Light blue, maybe. Light blue. And I want to draw the grid line so I get a sense of, you know, where we're looking at things. And I want to center the plot on the paper. So I'm going to use -x center and -y center. And that's going to center the plot on whatever page size I use. And the only thing is missing here now is the map projection. And let's see, I can drag this a little bit longer here, just in case I need. So we're going to use the -jg for the orthographic projection, which takes a longitude and a latitude of the point you're looking at, and then the size. So if I wasn't making a movie and I wanted to make a map that showed what it looks like from Earth for, let's say, Paris. And Paris, I can't remember the longitude for Paris, but it's close to 0 because there was a huge feud between the Brits and the French back in the day where 0 meridian should go. So let's call it 0. Latitude of Paris, I'm making this up. What might be in the 40s, right? Let's say 40, 45, I don't know. And then I would make a 12 centimeter movie. So if I save this, in fact, we could do this. I'm going to save this. And if I run my bash earth.sh, I get, oh, it's not too bad. I get the map, right? This is what we did yesterday. Not a movie, but we got a map. So that's sort of the building block. We're gonna experiment with making this into a movie, and doing exactly what I did now. Sort of thinking in terms of, what would one frame look like, is a lot easier on the head because you're putting in actual values for the longitude, latitude, and all that stuff. And you can make this plot and say, yeah, that looks pretty good. I don't like the colors. I can change the colors, and so on. So that's good. So this plot, which looks probably tiny on your screen, looks something like this. So all good. But this script is not going to change the location of the point on the Earth by itself. So the trick here is we're going to change the longitude, right? So we want the longitude to vary as the frame number vary. And I mentioned we have a variable that actually does this. So as the frames change, so movie going to run this script and it's going to change the frame numbers. We want to use that frame number as the longitude. And that's a shell variable. So I'm going to enter it here as $, and the name was movie frame. All right, so now I have a variable that is not set. It's undefined. It's just a random variable that doesn't exist in my script. So if I try to run this, I save this. If I try to run this, what would happen? Nothing good. Oh, I get an error message because I forgot to pass longitude to -jg because $ movie frame is not set. So it's like missing that entire argument and everything breaks down. So we can't run this script ourselves. We need help to do this. And the help is going to come in the form of the GMT movie command. So the movie command, let's see if I have that. I'll open that up. GMT docs movie. Okay, is this big enough font that it actually seems visible? I think so. So the movie command has, like many GMT tools, lots of options. Don't be intimidated by that. But if you need to know anything about any of these options, and we aren't going to use many of them, you will find them here. And there are some examples at the bottom of how to make a simple movie. But what we need to do is we have to specify certainly we'll go to the top here, anything that is not in brackets in these man pages are required, right? So you can see it, GMT movie takes the main script, it's required. It takes the -c to specify the canvas, the size of the paper. It takes a prefix name for the movie, and it takes how many frames are you building, or some more complicated input through a file. And then things get into brackets, so they're optional. So I'm going to try to make this as simple as I can. And I have to run this command on the command line, and it will read this script. But to keep things sort of simple here, I'm going to type my movie command as a comment into this script here. So the comment means, it's just a comment. It won't be run, but I will copy and paste the command down to the command line and run it. So we're going to run something called GMT movie, and it will take as an input file the script that we just wrote, which is earth.sh. The canvas option is required. It says, what's the dimension of your movie? And you can do things like HD or 4K, or you can do a customized 2 by 2 inches movie. That's okay. We're going to do the 360p, which is a widescreen format. So now I know that the page is 24 centimeter by 13.5 centimeter. So that lets me know how to compose my plots. And that's why I chose 12 centimeter there. I mean, that's going to fit in the 13.5 centimeter wide, tall paper. And how many frames? Well, we said we're going to do 91 frames. That's going to take us from 0 through 90 in longitude. That's 91 frames. And I'm going to give it a name. I got to give it a name tag, and I guess Earth is good. So -n Earth. These are all required options. And then the rest is optional. The first thing I do when I make a movie is that I want to make sure a particular frame, it doesn't matter which one, looks as I expect. Because nothing is sadder than to run this thing for 4 hours and find that none of the frame worked. You completely got the wrong colors. Your plot is not even on the window. You wasted 4 hours to learn this lesson. That's too long. So we have an option to just create the master frame. And the master frame is a particular frame that you choose. I'm going to pick frame number 55. It obviously has to be between 0 and 90 here, because you have 91 frames. And I want to see what a PDF version of that, go away, Microsoft, what the PDF version of frame 55 might look like. And I am not making a movie, so I'm going to say F none. So F is used to specify if you want to make an MP4 or a WebM movie, but I'm not making any movies yet. I just want to make sure frame number 55 should rotate the Earth 55 degrees and show it to us. So I'll save this. It's a comment. I'll have to copy and paste this comment down to my terminal down here, so I can run the GMT movie command. And if there's no typos or other errors here, this should actually make a plot. Okay, I noticed this. This is not, this is something with my system here. It did create the plot. You can see, I'll blow this up here. You can see that the central longitude now is somewhere in here, which I guess is about 55 degrees. So it has to rotate it. So when movie ran, and it ran on this script that has this variable movie frame, clearly movie replaced this name with the value 55 and then ran this script. So we created this thing. And you can see this is basically a snapshot of frame 55. So there's a lot of white space because I deliberately chose the pre-made 16 by 9 kind of movie format. So but I centered the plot in the middle of it. So you can see the plot is perfectly centered. And it looks like it worked. So if this is one frame, then all the frames should work, right? Because it's the same script, just different longitudes. So I think we can try to make a movie. So I'll keep this line here as how to make one of those master frames. I make a copy of my comment. The second one here, and I'm going to work on this one to make actually a movie. So I'm going to take out my master frame because I don't need to see it again. And I'm going to change the F option to MP4. So when I run this now, it will run over all the 91 frames because there's no limitations on that anymore with -m. It will run this frame script 91 times with slightly different parameters. It builds 91 PNG images, and then it will use FFmpeg to assemble all those images into an actual MP4 movie. So let's see if this works here. We hold our breath, make sure nothing weird has happened in the meantime. 3, 4 seconds, 5 seconds, 6 seconds. Okay, after 6 seconds, I get a message from Movie that it's running FFmpeg. With all kinds of cryptic options that the FFmpeg program needs. If you look at that, you can make sense of some of these options. Frame rate 24. Yeah, that's the default. I didn't specify anything about frame rate. So that might be a little bit fast for us, but there's something about Earth subfolder that and with PNG files, that must be where all the files are. And then the rest are gibberish. And then there's earth.mp4 at the end. So that must be an output file. So if I look in my directory here, I see I have a directory called Earth. If I do an ls on Earth, I see that I have 91 PNG files. I can go into that folder and open, Earth 34. And that is one of the actual raster images that is frame 34. So that's the size of my movie, right? It's 360p, so it's 360 scan lines. That's it. And it took me 5 seconds to run this command on my you can't see it here, but there's a Mac trash can in the corner here that has 24 cores. So Movie will run this script in parallel on as many cores as you have, and then assemble things. So the more cores, the faster and the longer movies you can run in less time. Okay, let's see if we made an MP4 movie here. So I have an Earth. There we have Earth MP4. I can open Earth MP4. On your operating system, you may have to start a program to open the MP4. Depends. You all did this exercise before installation, so I know it worked for you. And here's my movie. It probably looks very tiny on your screen. I'm going to try to stretch it up. It gets ugly and pixelated, but there it is. And I'm going to play it. And magic, we have made a Hollywood movie. You can make lots of money selling tickets for this one. If it wasn't for COVID, of course, you can't really do it now. So that's the basics of making a movie. Before we make a more complicated movie, we'll try to add some embellishments to this movie plot. So it would be nice to have some feedback of how many frames are we working on, what's the frame number, maybe some sort of indicator bar of how how long is this movie? Is it going to be playing forever, or is it just a few seconds? So we're going to try to do this. And if you look at the GMT movie, and you should look at this man page on a rainy day when you're thinking about making movies, you'll see that there's options for adding title pages before the movie plays. We're not going to do that. And they can fade in and out. There are options to paint the whole canvas with a constant color if you want to have a different background. There are options to fade in and fade out at the end of the movie of some sort through a different color. There's a bunch of label options. There's a label info option, and there's a progress bar option, among many other things. So we're going to play with those two options. So the label info, you can label different things. You can label the frame. So that's pretty simple. You can label elapsed time. You can label the animation time that you actually are trying, the phenomena that you're actually trying to show. It may actually have an absolute time. So we'll do this in the next exercise. But for now, we're just going to put a frame counter. So the frame counter is simply capital -L and then lowercase f. And the rest of the modifiers has to do with where do you want to put this label on the plot? Well, we will trust GMT to not do something stupid, and we'll just ask it to put it wherever. So minus capital LF will add a frame counter. And then for the progress indicator, P, automatic placement of progress indicators, repeatable up to 32 indicators. That seems like overkill. We're going to just do one. There's a whole bunch of different project indicators called A, B, C, and so on up to F. And they're different types. And I think we might have down on the man page here, there are progress. Okay, so here's, you can see the progress indicators A through F. So you'll pick one that makes sense for your plot. So if you have, actual time or data or something, maybe one of those time axes bars makes sense. If you just have, percentage completion or something, maybe A, B, or C works. So I'm going to do A, which is the little pie chart that's going to grow on us. So that's capital P, lowercase a, minus PA. And that's it. And I'm going to remove. So depending, again, on your operating system and how things work, it's probably best to remove the previous folder with images if you're not going to use them. So I'm going to remove RM minus RF, Earth. And I'm also going to delete the previous MP4 movie, because sometimes FFmpeg doesn't like to write to a movie that already exists. All right. So if you find yourself running this again and again, you can use the -Z option for zebra on GMT movie, and it will wipe away all those directories after it completes the MP4 movie. But I'll do it manually here. Okay, so I'm going to copy this command down again and see how that changes. So for me, it will take a few seconds. And there it goes. And I will open my movie. And I gotta stretch it a little bit so you can see. Can we see any? Okay, so there's the movie. You can see it has 2 zeros up in the corner. That's frame 0. And it has a washed out green sliver up here because I stretched a very low resolution image so you can see it. And it's a tiny little sliver of pink in there. So when I play this, you'll see the numbers change and my pie chart goes to 100%. So if you want to place these things in different areas on the movie, you have to look at the man page for -L and -P. It's pretty simple. It's like any other thing like color bars and whatnot. You can adjust it in the corners of the side, or you can specify exactly where you want it. So that's sort of the very basic example of a movie. Get you going. What I want to do next is to move into a slightly more sophisticated movie. If I can find it. I can't find it. Oh, there we go. So if you march along here, we're going to plot some points. So right now we didn't plot any data. We just showed the Earth, and it didn't really change, except we changed the viewpoint. That's the only thing that changed. Now, often you want to plot data points on a map. And again, for this not to be a boring movie, you want the points to change, or the number of points to change, or maybe points will come and go. So since this is a Geodesy workshop, seismicity is an interesting data set to plot. We know earthquakes happen at certain times, so you don't want to plot the point before the earthquake happens. And what happens after the earthquake is sort of up to you. Does it live on forever, so you can see all the quakes since 1960? Or should they only be there for a little while, and then you want to fade them away because the plot gets too complicated? To do those kind of things is really, really difficult if you're writing a just simple script yourself. So we wrote a tool called events, which you can think of like plot. It will plot symbols, but it uses the time information to only plot those symbols that should be visible for each frame. That's the hard part. So just try to be brief about this. You can read the man page for movie and event in more details, but you can see it's the time axis here, and that's T sub B is the beginning of the event, the green curve, which shows the symbol size. Symbol is 0 size until that time, and then it jumps to a 1 size, whatever that is. And then it can stay on forever, or it can stay on for a little while, or it can fade away. Oops, I hit this sensitivity on my mouse. So you can sort of control what happens when an event actually comes into frame and how long does it stay? 5 seconds or forever or just 2 frames. And then it can fade away. You can also change the size. It doesn't have to be on off. You can blow it up in the beginning, which we will do, and then it'll fade away after some time. And so these kind of functions, if you will, as time is attached to every single event. And as time goes forward, the event will go through this life stage of being larger or smaller, not show at all. And the same kind of scheme is applied to the color intensity. So you can magnify the intensity of the color briefly. You can also control the transparency of the symbol. So it can come into play slowly or fade away slowly versus abruptly. So we're going to try to put this together by making a movie of all the seismicity in the Pacific Basin in 2018, because we had a lot of interesting events in Hawaii. We had that eruption for 3 months, and we had a lot of interesting quakes. But that's in the context of the whole Ring of Fire. So to do this, we will obtain seismicity for 2018, magnitude 5 and larger only. So that's our data set. We're going to still plot maps like we just did. And we will plot the background map. And then we're going to plot the events on top of that. And then we're going to spin the Earth across the Pacific while we're plotting these quakes. If we had more time, and you have time after this course, you can put a fancy GRD image background instead of just a dumb coast map. But it takes longer, right? Because the GRD image command will run a little bit longer, and you multiply that by a few hundred frames, and you're talking lunch. So we're going to do it very simple background. Now, this last slide here is how to get those earthquakes. So you can go to USGS or any other provider of quakes and find their webpage and use their search tool, all that stuff. But that requires you to actually go to those web pages and find the search tool and click on things. Many of the providers allow you to set up automatic URL queries. And this gets a little tedious to do by hand, but once you get it, everything works. So I posted my script called get quakes on the GitHub animation folder, and you should definitely download that and use that one and run that in your workplace. Okay. If for some reason that doesn't work, I have uploaded the result, which is this quakes.txt data file on the GitHub page for animations. So I'm just going to switch to showing you the, let's see, I want to open, okay, we got to open this file. New file. Oh, I don't have that there, sorry. Let me get my getquakes script. Okay. Open. Getquakes, okay. So this script has a lot of comments here to explain what it's doing. But basically, we're building a very long and awkward URL. So we don't want people to type this thing in, right? Because there's like 80% chance you're going to have a typo and it won't work, and it's very frustrating. But basically, you can see what it's based up. It is the URL to the USGS earthquake server. That's the first line called site. I use variables for this. The time variable that I create just passes the information that this query needs. So it has the particular syntax, and we're going to get all the data from 2018. That's what that line says. The mag line says we only want quakes 5 and up. And the order is, we want to order them by time ascending. And then I put all that together into one very long variable called URL. We pass that variable to GMT convert, which will go on the web and download, and it will run this query and get the results back. And then we will pull out the columns that we need so that we can plot it in GMT. So I'm not going to go and dissect this command in detail because it will take a little while, but we're basically making sure we have long, lat, depth, and earthquake size, which I scale from magnitude to a physical symbol size, and that's my quakes.txt. So if for some reason your internet is failing and you can't run this script, you can just get the quakes.txt from the GitHub site instead. But in that case, you have to run these two other smaller commands. So one creates a standard CPT for seismicity. It's going to create a red, green, blue for 0 to 70, 70 to 300, and 300 to, well, 10,000 seems like a upper bounds on the Earth diameter, right? So it's anything deeper than 300. And then I no longer just want to create frames from 0 to 90 and use that frame number as longitude. I actually want to control a couple of things. I want to control the time for labeling purposes, and also which longitude do I want to show? Because now I'm in the Pacific. I don't want to start with 0, which is in the Atlantic, right? So this GMT math command is saying, create a file that goes from January 1st to December 31st in 2018 in steps of 1 day. That's the unit. So I have one here, and this is the unit. And then there's a little bit of black magic here, but I'm basically normalizing that 365 days to 0 to 1. And then I'm scaling that by 40, and I add that to 200. And that's why I create longitude that goes from 160 to 240 or something over the time of 1 year. And that's my data file times.txt. So I'm going to run this script, bash get quakes. Hope my internet connection is good. So it says downloading this thing. Okay, that was fast. And now my directory should have several files. It has a quakes.txt, good. It has the CPT file for this particular use, and has the times.txt. What does these files look like? I'm going to head times.txt, and you can see it's just a 2-column ASCII table where the first column is the date string for each day, and the second one is the longitude that I computed. So I said it's going to go from 160 to 240 over those 365 days. And if you do a tail of times.txt, you can see that I end on New Year's Eve and I end with longitude 240. So in between, these are linearly varying. Okay, so now we're going to actually make the plot. So I'm going to need a new script here and the usual shebang. We're going to do a GMT begin. We're going to make a plot again. GMT end. Show. Okay, what are we going to do here? Well, we're going to do the same thing we did for the first exercise. We're going to lay down the Earth plot. So being a bit lazy, I will copy that command from the previous plot and paste it into this script. And I'm going to make some changes, but this will save me some time. Because I'm going to do very similar things here. I'm going to do a global map. I'm going to paint the background with some colors. I'm going to draw the line. I'm going to center my plot. All that is fine. But I'm going to plot red, green, and blue symbols. So this light blue is probably not a great color for oceans. So I'm going to change that to light gray. That seems reasonable. Oh, sorry. There's the bar. Now, the longitude is no longer the frame number. I'm going to want to use the second column in my times file to be the longitude, right? Not the frame number, because the frame number integer is 0, 1, 2, 3, 4, 5. I want this to go from 160, 160.219, 160.4, so on, right? So I have to pull out those columns where the rows corresponds to my frame. So that's the magic of the movie col1, right? So I'm going to pull out movie col1. So 0 is the first column, 1 is the second. I know, this is how it is. So that's going to give me the longitude automatically. It's going to be fed into this script by movie as it runs these things in parallel. So that's sort of similar to the first part we did already. It's just a different variable. Now the trick is to plot these quakes. So we're going to use not plot, because if I use plot now, I will plot all the quakes on all the frames, and the Earth will spin around with all these quakes. That might be nice, but that's not what we want to do. We want to actually pop up the quakes when they happen. So we're going to run GMT events. Okay, what's GMT events? Spelling events, there we go. Right. So again, here you see those time curves that are attached to each symbol. So one for intensity, one for size, and one for transparency. And they're defaults for these things. And then it takes the usual minus J minus R symbol. And then there is this thing, time now, because this is going to make a snapshot at a particular time, and it's going to use that time to examine the data table to see, so which of you guys going to be actually visible during this time? And that depends on these other settings of, obviously if the quake happened before that time, it should be represented. If the quake is in the future, we're not plotting it. So that's what's happening in the events. So I'm going to do a command that I know sort of works. We're going to read quakes.txt. That's the input data. Right. That's the whole data file, of which only some parts will actually be used for a given frame. Then we're going to color these symbols based on depth. We created a CPT for that called quakes.cpt. It's a sort of nonlinear boundaries, right? 0 to 70, 70 to 300, 300 to the center of the Earth. And so that's going to be the coloring. And now T, which time are we plotting this for? We're going to remember we're going to run this at a particular time, so only the quakes that should be visible are visible. Well, so this is abstract. We're running a single script, but the script's going to be called, 365 different times. And our job is to understand that, well, I created a time file. It's called times.txt. So just like I did the movie column 1 to get longitude, I will use, I'll be lazy and copy. I will use movie column 0 for the time, right? Because that has the right time that is keyed into the data table. The data table, which we didn't really look at, head quakes.txt, you can see that one of the columns is time. So longitude, latitude, depth, and symbol size, magnitude scale to kilometers to make a symbol size, and then the time of the quake. So that's what event's going to read. We're going to plot a symbol. And since we're plotting a spherical Earth projected that has this perspective view, I'm going to plot the circles as degenerated ellipses. So it's going to take the dimensions of the symbols in kilometer and plot an ellipse. It will be a circle, but as the projection and the view changes, they will be stretched into pancakes that are wrapped on the Earth. And then I have to tell events that we're doing a time data here, and it needs to know what the time unit is, because the default is actually seconds in GMT, but we set everything up to work with days. I do a line break there. If you do a line break like that with a backslash, you have to hit return immediately. If you add a space or anything after that thing, you're in for a lot of grief. So make sure you have a clean return after the line break. Now, now the magic has to do with these 3 time curves that are attached to the symbol size, the color magnification, and the transparency. So I will type in one set of options that work. We can try to dissect them a little bit. So the symbol size, M sub s, I want it to magnify itself up by 5 when the symbol first arrives. And then when it finally is died down, I want it to shrink a little bit because I don't want it to take up all the space. So the symbol's going to come on 5 times as large, shrink down to normal, and then go down to half after a little while. For the color, so the color is set by the depth through the color table, so red, green, blue. But when the symbol first comes on, I want it to be visible. It's going to flash up with kind of washed out color by intensity 1. And then when we go into the coda after the symbol dies, I will actually do the opposite. I will darken the symbol, so negative intensity. And then for the transparency, MT, I will at the coda, I will set the transparency to 0. So they will they should be visible, but small and dark. And then we have to set up this time function, this complicated thing with many knots. All right, so there's an E option for specifying that. Neither I nor you will remember these things, right? So you have to go to the events page to see, how do I specify how long should this initial pulse last? How long should the signal last? When does the coda start? So I'm going to set this up for the symbol size here. I can have a rise time of 2, and it's going to decay after 6. This is days. And that's my script. So I'm going to save this. I call this quakes.sh maybe. Oops. Try to spell quakes.sh. Too many S's. There we go. Okay, I'll save that. And just like before, I'm gonna type in the GMT movie command here. It's, as before, it's gonna read the name of the script, which is quakes.sh. We have to have a -n to set the name. Okay, quakes maybe. And we have to specify canvas, basically the movie dimensions. Again, we'll be cheap and do 360p, which is a small, short movie, or small in size. And instead of specifying, so -t is required, right? But instead of specifying I want 50 frames or 2000 frames, I say read the file times.txt, which we created. It has 365 records. Those are the number of frames. And it has information about each frame. So those are all the required ones. And we start off by just looking at a single master frame, let's say frame 50 in PDF. And we'll turn off movie making, so F none. And I think that's the minimum I can get away with. I'll save this and copy the command. I don't think I made any typos, at least not intentionally. And I'm going to get that stupid message, but no worries. Quakes.pdf. Good. All right. So it basically seems to have worked. So we have the Earth. This is frame 50. I need to adjust my latitude a little bit. I just copied and pasted, right? So this was set for Paris, but for the Pacific, we should do something closer to equator, I think. So, but you can see for this time, there are a bunch of quakes. Some of them look disproportionately large and washed out. That's because they just happened. So they gone bang, they come in. And then you can see the smaller, darker symbols are quakes that have happened before this frame, before frame 50. And they already done their thing in announcement, and now they're shrunk away. So this worked, except I'm going to change my latitude from 45 to oh, I don't know, 5 maybe. Okay, so just look at my watch here. We'll try to wrap this up and I'll let you guys do more. I'll copy this line down. One more comment. We'll try to actually make the movie. So to make the movie, we take off the -m and we change the F to MP4. And since we're here, we might as well add a label. So I'm going to add label. We know that. We can do F for frame. We can still do that. But I'm going to do C for column. So I want to use column 0 in my time file, which is the first one, which has the time, to use that as the label. And if you remember that file format, it has the dates. This is ISO code dates, right? So year, month, day, capital T, and then there's a clock that all 0 because it's just 1 per day. And I don't want to plot all those zeros, so I'm just going to turn off the format for the clock. So this is sort of GMT options. Format clock map equals minus. Turn it off, basically. I'll stand this thing here. So if you don't do that, you're just going to end up with these 0 zeros. No big deal, the hour. But this will take that out, and we'll put this thing up here. And, well, why don't we do progress bar B, since we're at it. There's only 2 letters. Okay, so we'll do this one. So this is going to now chug through 365 small frames with very little action for each one. So it's relatively fast, but it's still, 365 separate maps being produced and then eventually assembled. So this might take longer than 5 seconds for me too. We'll see, 5, 6, 7, 8, 9, 10, 11, 12. Okay, get with it. 14, 15. Should be done soon. Oh, there we go. So it's done. So it made 365 frames. If I do an ls quakes, my directory, you can see I have all these PNGs now. But I also have a movie called quakes.mp4, which, as before, is going to be kind of small, a little ugly looking. And we'll stretch the guy again so it's at least visible. And you can see the top left corner has the date stamp now. And the top right corner has another progress bar as a circle with a growing color. And there's no quakes on January 1st this year, but hopefully when I start play here, it will have some quakes. And there they are. So you can see what I mean by this popping in there. When they first happen, they sort of bang, and then they decay away. So they don't take up space for the subsequent quakes. Right. And it's going to go until the end of the year, and there we are. And the circle is complete, and we ended up with on New Year's. So this is a relatively sophisticated movie, a lot of stuff happening, and it's all done by 2 lines of script. Right? So since you all can read, I'm sure you can read the man page and try to get a handle. What the hell does this mean? Right? Well, it's compact language for passing arguments to those time functions, but it's certainly doable. So for the breakout rooms, it's kind of hard to start a brand new movie from scratch. So I suggest you do some deviation from what I showed you. So you could pick another time for earthquakes. You could don't have to do a spinning Earth. You can just plot an area near you and just plot the quakes there, because this got all the quakes, right, from the whole world, magnitude 5 and up, and make a movie of that. You can explore some of the other options in movie to add different labels. You could do the fading in, fading out if you want. And since you have a little bit longer time, you can change this 360 to, let's say, 720. That's going to probably quadruple the time it takes to finish the movie. So in my case, that's 20 seconds to 2 minutes. It's not terribly long, but again, that's with 24 cores. So it will take longer the fewer cores you have. But I wouldn't have to change anything about this script except this -c line to make a more high resolution movie, right? So the trick to make movies is to start very modestly with few frames, a coarse representation of the movie, and use the -m option to just look at the frame. Because if the single frame doesn't look good, there's no point going any further. So you stop there and you work on this script until the frame look right. So if you're making a map of your country earthquake, it's a PS Coast or a GeoImage job first to get that correct, right? And once it looks good, then you can start letting loose on these other items there. So I will stop talking and let you guys play with this kind of thing in the breakout room. Again, because it takes a while to run animations. If you start from scratch, do a very, very simple one based on some of these templates. Okay, and that's it for now. We can go into the breakout rooms, and I'll stop my sharing and play with this. Hey, there you're back. That's great. Okay. All right, folks. Good job so far. So according to the schedule, we have break is over. So we have a final project about an hour for you to work on. And the way this will work this year is that you will be sent back into your break rooms, and you can choose the project that you want to do. So some of you may want to plot your own data in your area. Some of you might be inspired to make a movie of your data. Others are trying to complete some of the homework assignments or some of the tests. It depends on where you are on the very long, steep ladder to reach supremacy and how to use GMT. So you pick a thing that you can do in an hour-ish, and then when you have finished and you have a finished product, please post it on Slack with a short caption that explains what it is, and we will assemble all these into a final document for all to see on Google Docs. And we will help you with questions during the project, and then we'll bring you back here in about, I guess we'll do an hour, 50 minutes, and we'll just do a little wrap up at that point for the whole course. Anything I forgot to say, Leo? It's about that. So yeah. Please go into the
sharing the scripts.
Yeah, sharing the scripts. Sorry, too. So share the scripts as well in your Slack. You can, if you're fancy, you can actually format your script using the, I guess it's the open close triangle button to make it make it a script.
Yeah. So on the Slack, there's a little lightning bolt icon next to the chat window, the message window where you type. So it should be on the bottom left of that window. If you click on that, there is a create code or text snippet. So that lets you make like a little code snippet that appears on Slack. So if you want to share your scripts, that's a good way to do it.
Yeah, thanks, Leo. That's better than what I'm going to say. Okay, so Melissa, you can set up the final breakout rooms, and we will try to keep track of everybody's projects. It'll be wild.
We should slowly see people coming back. I just closed the room.
Okay, thanks.
Are we supposed to be handing in the things we did, those during all the break sessions, or not?
No, you don't have to do that. I think if you can post a final project, then that will be it, I think.
Okay, so I'm working on the final project. I'm trying to make a movie of a big earthquake and its aftershock sequence. But all of my earthquakes are coming out huge. I can't get the size down.
That's a size issue, yeah. Yeah, there's, it doesn't have to be done in 3 minutes. You can post it later today or even tomorrow. I think we're not going to, we have the GMT SAR workshop, some of us, next 2 days. So the timing of, wrapping things up for us is a little longer. So just
right, well, I'm in that also.
Yeah, exactly. So no sleep for the wicked.
No.
So you say it's allowable to post it later. GMT Coast isn't working right for some reason. So I'm
yeah, you can post
why it's doing that.
Yeah. I mean, we're rushing everybody really hard, so we don't
Yeah.
expect everybody to have everything done on time.
Yeah, all I want to do is print the country boundaries, and it's stubbornly refusing to do that. So I have to figure out where my error is.
Yeah, we can help you if you post it in the Slack channel.
All right, I could do that really quick, and I want to add some custom symbols too. But right now, I'll go with this if I can.
Yeah. Okay, so everybody's back from the breakout rooms, and all the instructors are here, and they're all happy that we're at the end of this 10-hour little session that we did. So first, I want to thank the instructors who stepped up. You know, their $2,000 per hour pay was cut this year, so it's down to 0. So it's all free. So they're all volunteering their time. So I want to thank them, especially folks who are staying up really late in very odd areas of the world. So thank you guys. And thanks to all the students who put up with us. You know, that's 10 hours of us making bad jokes and horrible GMT syntax. It's a lot to take. But it builds character. It's really important that you can put up with frustration as a scientist. I mean, if learning GMT breaks you down as a scientist, then, you know, wait until we have real science problems to tangle with. So this is just a nice little start, I think, on being a scientist. We are going to leave the Slack channel up for, you know, it's not going to go away, but we'll probably not be monitoring that as much. So if you want to continue the discussion with problems you find, please use the forum, the GMT forum, because that we do monitor, and that goes on forever. And as we said, if you do find actual bugs that you're comfortable as a bug, please open an issue on the GMT GitHub site as well, because that's where we deal with bug fixes. So we love to hear from you in either of those two forums going forward. You already pointed out a whole bunch of problems in GMT that we need to work on. So this is good for us too. We learn from you, because there's nothing better than fresh users being exposed to GMT and breaking something that we who are experienced would never do, right? So we only learn by having people try the code in different contexts. So as we mentioned earlier, we would like you to post a final project of some sort in the Slack channel, ideally with a little script snippet, ideally with a caption. And we will collate all those and make a final document. I think that's the plan, to make a final Google Docs, so something that will live on the UNAPCO server after this course is over. We are still dealing with finalizing all the video recordings. So it's going to probably take a day or 2 or 3 maybe before they all get up there, but they're all going to get up there. So you can always go there and replay all the sessions and if you missed anything. And all the, you know, all the material will be on the GitHub site, and also I think duplicated at UNAPCO. So we know this is a rushed workshop. This is normally a 2-day in place with people there, and we can talk to people at night because they stay in the same dorms. I mean, it's just a much vaster landscape. and here it's like just a few hours, and then you're into the break room and you're a little bit lost. So we understand that's still frustrating, but, you know, hopefully in future years, there might actually be real workshops again with people. That's the hope, but that couldn't happen this summer. That's sort of what I have on my list of things in my head to mention. Anything really important that I left out, guys? No, it seems like I hit all the right things. I mentioned where to put things, where to go next. In addition to, you know, complaining about things not working or needing help with things, if you find certain things are working in an awkward manner, let us know that too. Often we will implement changes to the code to fix something that is awkward, because, you know, none of us like to type 5 lines if 1 line works. And lots of changes in GMT comes about by people asking for feature requests. You don't have to be a coder to write a feature request. That's just, hey, can we do this? And it either can be done, or it is really hard to do and it may not happen, or we disagree with you. That's okay. But, you know, very often those feature requests are really good, and we are very excited about implementing them. So think about that. Anything that you felt were awkward and could be done better, just tell us, because we've done this so long that we can't always see that, right? We're just way deep in the forest or down in the mine, chugging away in the C code. So should not be left up. So with that, I think we are. Yeah.
Sorry, just to complement that as well, one thing, so you can ask for features in the code, so things that you find that don't work quite right, or that feel a little bit awkward in the code, but the same is also true for the documentation.
Yes.
So if you're looking at the documentation and there's a part that you just cannot decipher, that's probably not on you. That's on us for not really explaining it very well. So pointing out where these faults lie in the documentation is the best way for us to actually go in and maybe clarify it or make it a little bit more explicit. Or even if you yourself end up figuring out the solution, you can propose like, oh, it would be nice if you reworded this way because that's more understandable. So we really do need a lot of help with all of this because it's a large project with a very small team.
Yes. Yes, and documentation is something everybody can contribute to. It's just plain language. So yeah, that's in fairness to the developers, that's sort of the least exciting part to write, and also they're partly know the problem too well to write a good documentation. Sometimes they take shortcuts because they know how things work and they don't think of explaining something. So that's what you're looking at. It's kind of very terse documentation meant for other developers and not so much for normal people. So yeah, think about that too.
And if I may add something, continuing what Leo said,
yes,
about the size of the team, please feel free to hang on the forum, because first, if you know, you can help others as well. And also, for example, I participate in a couple of forums where I say nothing because I don't know enough, but I learn quite a bit seeing questions from the others. So if you have some time and interest, please keep an eye on the forum, and in case you know, well, help others as well, because if you are more to participate, people will wait less for the answers. Sometimes we are quick, other times you are not so quick, and people may have to wait a day or two for an answer, or even get forgotten, which also happens. So please, if you have pleasure in that, would like you to participate on the forum too.
Yeah, that's very good. Yeah, so we need all the help we can get, obviously, and we're all in this together. We're all in the same community. Community is only as strong as its members, right? So if we all help a little bit with what we can, then we make a better product and a more useful product. So with that, I think I will again wish you a good night or a happy lunch or whatever it might be, and hang in there and work on your project and keep posting questions at those forums that we gave you. And we'll hope to see you in real person at some future meeting. And if not, maybe the next Zoom conference. Who knows? So signing off from Honolulu, Hawaii. Have a nice day or night.